Yeah.
Okay, good. And let me just get this right. All right, then we switch orders a little bit and welcome everyone back then to the next presentation. Mike, if you want to introduce me, go ahead. Else, try to fix the screen. And I just go ahead. My name is Manuel. I'm a professor here at the Humboldt University here in Berlin. And I would like to reconsider in my presentation some of the standard and maybe not so standard approaches to causal inference from a continuous time perspective. So this is something we're doing quite some work on. And if you do have any questions, please just go ahead and ask also in the middle of the presentation. I really appreciate this. What I would like to do with you, I would like to reflect a little bit together with you on the role of time in the graph-based causal models, also the graph-based causal models Christian was talking about. And I would like to offer a, I'm not sure it's a different, but it's an alternative, maybe complementary view on causality, a mechanistic view on causality. And I will briefly introduce you to the idea of local independence graphs. And these local independence graphs, which have been proposed in the literature, will lead us very naturally to continuous time structural modeling. And here I will first, you see, I put the structural in parentheses. So I will first focus on the statistical aspects and talk a little bit about the theory of continuous time modeling, the statistical modeling, software, and some developments, before then coming back to the structural part, so to the causal part. And here I will essentially raise the question, quo vadis, where are we going? Because I don't know. So at that point, you will see the loose ends of my presentations. First, because I just don't know better. So there are some open issues. But then second, also, that this is the hope that we will be able to come back to this in the discussion. And there I appreciate any insights or thoughts you may have. But first, a short recap. In Christian's presentation, we have seen that there are at least 3 key assumptions underlying the graph-based causal modeling approach. The first one was that we have a correctly encoded causal structure, for example, meaning that the direction of the errors is correctly specified. Then the second one is what's variously known, and Christian has alluded on this as autonomy, stability, modularity, invariance, essentially meaning that if you intervene on a level of a node, this doesn't affect the relationships among other nodes. And then the assumption of no interference, so that an intervention of one individual, usually in the standard setup at least, doesn't affect another individual. Now, if these assumptions are met, then we can use statistical approaches like the general cross-select panel model, which Mike will talk about in the next presentation, hopefully, to infer causal effects from observational data, usually given some additional assumptions regarding, for example, the parametric form or the distribution. Now, here's a much more simple example than the kind of examples Christian was talking about and Mike will likely talk about. Just 3 variables, say physiology, affect, behavior, and more specifically, this could be something like the level of serotonin in the brain. It could be social anxiety, or it could be social withdrawal behavior, sort of a running example. And if this model is correctly specified, if that is the causal structure, then we can estimate the direct causal effect as well as the indirect causal effect. That's pretty straightforward. The situation changes, obviously, as soon as we have an unobserved confounder in here, this variable u. Now, in Pearl's terminology, we open a backdoor path, and now we're no longer able to neither estimate a direct causal effect P on B, nor an indirect effect, because we have this vector path in here and A functions as a collider on this relationship. So with this model, there's just no way to actually estimate a direct causal effect or an indirect causal effect. Interestingly, though, the situation changes as soon as we change our measurement a little bit, for example, by measuring effect twice. Now we're in a longitudinal design. This changes our DAG. And if we now have the assumption that the unobserved confounder only operates on the first affect measure and on behavior, but not on the second, now we're in a situation with a different model because of a different measurement. And now we could condition on A1, which would block the backdoor path, again, in Pearl's terminology. And now we would be able to identify a direct causal effect as well as the indirect causal effect. So this is an example which shows you that measuring multiple times changes the DAG and opens up new possibilities. And depending on your perspective, this is something you may find very natural, that's just the way it is, or you may find a bit worrisome. If you find this very natural, and that's just the way it is, here's a second example, which you may find more worrisome. And in this example, let's imagine we have a researcher, and that's the DAG this researcher postulates. So a relationship between two variables observed over time, here at 4 time points, always with a time interval of 24 hours. So if this is the correctly specified causal model, we can again use statistical techniques, as explained by Christian, to estimate our causal effects. And in that case, we may get estimates like this one. That may be a causal effect of P at after 24 hours on A at 48 hours. Now let's imagine we have another researcher who has exactly the same theory, exactly the same DAG, but the only difference is that this guy uses a different time interval, say a time interval of 6 hours instead of 24 hours. And now, most likely, the parameter estimates, they will change. We will not get the same causal effect estimates here. In that case, the autoregressive parameters will be a little bit higher, whereas the autoregressive parameter here will be a little bit weaker in the sense of closer to zero here. And that may be a problem because obviously there's no way of comparing these results directly with each other. So we don't know whether the parameters are different, whether this is due to different causal mechanisms, or whether this is due just to the time interval, or whether this is just random fluctuations. So this first example, this showed that changing the number of measurement occasions changes the DAG. And to me, this raises the question whether the causal model should depend on the measurement. And the second example has shown that changing the time intervals between the measurements does not change the DAG, but it will almost always change the estimates of the causal effects. And to this raises to me the question whether time shouldn't matter for the inference of our causal effects. And obviously, as always, I'm not the first one to think about these problems. There are a number of people who have thought about these things and published about these things. And what has been proposed in the literature is a somewhat alternative view, a mechanistic view, which is often displayed in terms of so-called local independence graphs. And the local independence graphs, they are also graphs, just like the DAGs Christian was introducing. But the most important difference is that the nodes of the graph do not denote random variables at a specific point in time, but they rather represent processes. And the edges between the processes denote local dependence relationships. And a local dependence relationship essentially means that if I change one variable, then we observe a change in another variable over an infinitesimally small time interval. So this will get a little bit clearer once we get to the math behind these things. But likewise, a missing edge would imply local independence, meaning that if I change one variable, then we won't see a change in another variable over an infinitesimally small time interval. But this doesn't mean that the two variables are stochastically independent for any given time interval. So local independence is not the same as stochastic independence for a given time interval. Another very obvious difference in these graphs is that the graphs are usually not acyclic. So you see we may have a relationship on P, here serotonin on social anxiety, and social anxiety on the level of serotonin. And that's this more mechanistic view of the world. There may be reciprocal relationships, obviously. And in some sense, this idea of local independence instead of stochastic independence or dependence for any given time interval can be seen, and I'm citing here, as a natural extension of conditional independence. So the sort of Bayesian networks, the DAG formulation, to a dynamic time continuous framework. And now that obviously raises the question, what the hell is a dynamic time continuous framework? And looking at the people joining in here, some people are working on this, so they are very familiar with continuous time models. Others may not so much be. And for those of you who have never heard about dynamic time continuous frameworks, let me give you a very brief introduction to the statistical approach of continuous time dynamic modeling. And let me start by doing so by adopting again the discrete time perspective. The kind of models Christian was talking about, where we have, say, two variables, x1, x2, observed at a specific time point t, at a specific measurement occasion u. So this would be measurement occasion u1, u2, u3, u4, and the time intervals may always be 24 hours, as an example. Now we can collect these variables in a vector. So here we would just have 2, but it could be more, could be just 1, could be 10. And we can collect them in the vector x here at time point t, measurement occasion u, and we regress this x on x at the previous measurement occasion. So a standard vector autoregressive cross-select model. Now in this matrix A dagger here, we do have the autoregressive effects in the main diagonal, and we have any cross-select effects in the off diagonals. And since this relationship is typically not deterministic, we will also have a stochastic component here and a prediction error term. Now what we can do mathematically, that's straightforward. We simply subtract xtu minus 1 from both sides of the equation. That's very simple. So now we're looking at difference in x across two measurement occasions. And this is the basic idea, for example, of change score models, or if these variables are latent, then this is latent change score modeling. So it's just a reformulation, essentially, of this kind of a autoregressive cross-select model. And we often write this as delta x. So delta x is now the change in x across two measurement occasions. And now we can divide this by the length of the time interval that has passed between these two measurement occasions. Here, for example, 24 hours. So now we're looking at a rate of change, which we're predicting here. And usually in latent change score models, if you're familiar with these models, we often simplify things by saying, well, delta time is just 1, therefore we can get rid of this. But it would be more precise and often a more appropriate procedure actually to look at the actual time that has passed. So we're looking at a rate of change. Now we can take this equation, that's just the same equation, and in continuous time modeling, what we do, we now hypothetically let the time interval go towards 0. So we're making the time interval over which we're looking at change smaller and smaller and smaller, so that this rate of change approximates a derivative. We're looking at change in x over an infinitesimally small time interval. And this is our dependent variable in continuous time modeling. Now we can write this, and if you divide by dt, that's just a different way of writing things. If you divide by dt, then you see this is the derivative we are predicting here, and we predict it by x. So now x is a function of its own derivative. We're looking at a differential equation. But just like before, this differential equation typically won't describe a deterministic relationship between x and its change, but rather a stochastic one. So we also need an error component in here. And this here, usually we're assuming a random walk in continuous time. So this is a so-called Wiener process. In this formulation, that's an example of a very simple stochastic differential equation, which is also known as an Ornstein-Uhlenbeck process. And this could be one statistical representation of such a local independence graph. where the local independencies are now captured in the A matrix. So for example, here we don't have a relationship. We have local independence between P and B, which would be captured in the A matrix by the zeros in the upper right corner and the lower left corner. And if, and again, I'm quoting here, I'm citing here, if the differential equation is structural in the sense that changing an element of A does not change the other elements, then the local independencies which we have in here are causal. And this is good news. If we believe in this, this is good news because now we're on familiar territory, because we know quite well how to deal with these equations. And statistically, this is something we, but also other people have done quite some work on. So we can take such a stochastic differential equation, Ornstein-Uhlenbeck process, and expand it in various ways. So for example, we could add intercept terms in here, we could add input effects in here, but we always have a differential equation we start with. If it's a linear differential equation like this one, then we may even find an analytical solution. So we can solve this differential equation for an initial time point and for a given time interval. And then we can go ahead and constrain the discrete time parameters in our discrete time model, because our measurements, they will always be discrete. I always measure discrete, but I can constrain the parameters in the discrete time model to the solution of the underlying continuous time model. And then I can go ahead and estimate things using either frequentist or Bayesian methods. Now, obviously in step 2 and in step 4, that's where the math comes in. So that's where the ugly constraints are coming in. And I brought lots of equations with me. So if you're interested in the maths, then we can talk about the math later on. But conceptually, this is exactly what we're doing in continuous time modeling. Now, the good news is that these constraints, they're all known. They're all in the literature. Mathematicians have all solved these problems decades ago, essentially. So it's all out there and you can easily implement it. And the even better news is that this implementation is already done for you. There are various packages. One package is the CTSEM package, which we have developed. And here credit really goes to Charlie Driver, a former doctoral student of mine who, as part of his dissertation and then postdoc work, has pushed the CTSEM into a quite powerful, I would say by now, package, much better than the initial functions we have had. And this is documented. You find this in the Journal of Statistical Software, for example, in 2017, or just look at the help functions, look at CTDoc functions. There are quite a number of documentations and manuals on this. And this is, if you don't know this, by the way, this is the logo of the Journal of Statistical Software. So we figured if you're writing something on continuous time modeling and there is a journal out there which has these melting DALI clocks, then it has to be this journal where we will publish this. So we were happy once it got accepted there. Now, I'm not going to talk too much about CTSEM, but just if you look at it, it's on Crane, and if you try it out, don't get confused. Originally, there was just one CTSEM package, which was either interfacing to OpenMX, a general SEM package for frequentist estimation, or to STAN for Bayesian estimation. But recently, the package was split into two packages. The main package, which will now always interface to STAN, and then the CTSEM OMX function, which will interface to OpenMX. So depending on which one you want to use, but both versions are open source, freely available, and on Crane. And the way they function is also, at least at this conceptual level, the same. We have a CT model command with which you can set up a model. It may either be a very simple model like the one we have seen, or it may be the kind of general cross-leg panel model Mike will be introducing later on, and we can implement this in a continuous time fashion via this command. That's essentially setting up a structural equation model. Then we have the CT-fit command, which combines the data with the model and does the estimation either via interfacing to OpenMX or via interfacing to STAN with the CT-STAN-fit function. And then you can use the usual summary and plotting functions, for example, to produce plots like these ones, where you're looking at the autoregressive parameters or the cross-select parameters in discrete time as a function of the time interval on the x-axis. And here you see, for example, our two researchers again from the intro example, who were using different time intervals. Researcher A was using a time interval of 24 hours, researcher B a time interval of 6 hours, and they obtained different causal effects, minus 0.10, minus 0.25. But from this continuous time perspective, we see that the underlying continuous time model, the causal model in continuous time, was exactly the same. The data generating process was exactly the same. But we will not realize this if we only look at the discrete snapshots in time. And here we see this because the 2 points are lying directly on the same function. So it was the same generating model. And the same is true for the other parameters, obviously. Now, statistically, this approach is well known since quite some time, and it's out there, and it can be expanded in various directions. Some of them obvious, some of them not so obvious. Here's some of the work we did. For example, we can use exactly the specification to look at oscillators, at damped linear oscillators, or at coupled oscillating processes. The approach can be used for n=1 time series models, so the kind of dynamic factor models where you have lots of time points, but only a single individual or very few individuals, or for the standard panel models where you have lots of individuals, but only rather few time points. It can be generalized to higher order models, and maybe Mike later on will talk about higher order armor models. So that could also be implemented in a continuous time fashion here. And then recently there's different ways of dealing with heterogeneity. It has recently been used for meta-analysis to solve the problem of making studies that are using different time intervals comparable with each other. And it's quite flexible when it comes to modeling different cohorts like cross-sequential designs. There are different ways of incorporating input functions. So if you look at the literature, there's quite some stuff out there. And I'm just pointing you to this, that if you're interested and if you feel that there's that this is something that may match your research questions, then just let me know. And there's more specific references out there. So statistically, I think this is more or less established. When it comes to structural modeling and causal modeling, I'm less sure because I just don't know. So that's the Quo Vadis question here. However, I just feel that in the causal models we're talking about, we need to better clarify the role in these models and the role of time in these models. And this may mean moving beyond DAGs where time is not considered at all, over DAGs where time is considered in a discrete fashion, towards maybe such local independence graphs where we're looking at the processes in continuous time. And relatedly, I feel that we need to better separate the measurement from the mechanisms, because the measurement will always be discrete. So no matter whether you're doing EEG research or whether you're doing panel research, the time intervals may be different, but the measurements themselves are always discrete. You cannot measure continuously. But the processes, they are often, not always, but often, at least in our field, in the social and behavioral sciences, continuous processes. And the mapping of one onto the other, that's not straightforward. So for example, you could have a negative effect of, say, serotonin on social anxiety in a continuous time framework. And this may translate in a discrete time framework into anything between a negative effect, positive effect, or a zero effect. So let me give you an example here. Let's assume that this is the true A matrix in a continuous time fashion. So this is what Ahlen called the causal coefficients here, the drift matrix. And let's just focus on this coefficient here, the effect of serotonin on social anxiety. And it's a negative effect. And that makes theoretically sense because the higher the level of serotonin in the brain, the lower social anxiety. This is how our anxiolytic drugs are working. The selective serotonin reuptake inhibitors, something like Prozac. Now, if we look at the realization of this model in discrete time, so if we're observing things, say, over a time interval of 1 unit, then this is the effect we will get, an effect or one time unit of minus 0.3. So again, it would be negative. It would be minus 0.3 instead of minus 0.5. So maybe not too much of a difference. But if now from a continuous time model, we start looking at how the cross-lagged parameters change as a function of the time interval, then we will see that they may change quite dramatically and in quite different ways. So for some time intervals, we may actually see a negative effect. For other time intervals, it may just be zero, the effect, while yet for other time intervals, the effect may turn positive in such a trivariate system here. So depending on where you observe things, your conclusions, also your causal conclusions, may be quite different if you approach this just from this discrete time perspective. And I think this in itself is important, but it becomes particularly important, and that's my final point, if we want to understand the effect of interventions, and if we're thinking about maybe combining this mechanistic view of causality with the interventionist approach to causality by, for example, intervening on a specific variable at a specific point in time. So for example, by setting physiology or here serotonin to a specific level, say of 1 at a specific point in time, and then look at the effects. So if we would do this in this system, for example, we set serotonin to a specific level, say a level of 1. Now we're looking at the value of the dependent variable here on the y-axis. Then after a while in the system, we would see that the effect returns back to an equilibrium. We also see this intended effect of a reduction of social anxiety as a function of an increase in serotonin, say the administration of an anxiolytic drug, but only for some time. And after some time, the effect actually goes in the opposite direction. So we may see an increase in social anxiety as a direct function of the administration of an anxiolytic drug here. And I think this is something that we wouldn't see just from this discrete time fashion, but I think it's important when we're thinking about interventions. Now, obviously, there are a lot of issues with this approach. There are statistical issues. One, for example, relates to linear versus nonlinear dynamics. The kind of equations I have shown you were linear stochastic differential equations. They're quite simple, but people are arguing rightly so that the world is nonlinear and follows nonlinear dynamics. So we may want to adopt these nonlinear dynamics, but this makes it even more complicated to map this onto clearly interpretable effects and clearly interpretable causal effects. The examples I've shown you had very few variables, only 2 or 3 variables. And again, the world is multivariate, so we may need more variables. But if we include lots of variables, then we get really complicated relationships. And the model also gets quite complicated to be estimated. So we need to regularize, or we somehow make things simpler again. And obviously, people are working on this. And then it's the question of computation speed. If the models are getting complex, then computation speed goes down, and we are in this trade-off between somewhat faster frequentist methods versus slower but more flexible Bayesian methods, and we may need to switch forth and back here. But I think statistical issues, these are all issues we can resolve. There's lots of work ahead of us, but the direction is clearer, at least to me. That is somewhat different when it comes to causal issues. Here, even at the philosophical level, I don't even know whether this mechanistic view is really different, or whether it's just a complementary view, or whether we can combine the interventionist approach and the mechanistic approach. I also currently don't know the potential and the limits of the local independence graphs. Obviously, we cannot use the standard DAG-based rules and apply them to the local independence graphs. And there are different rules we can apply to them. But as of today, just because of my lack of knowledge, I don't really know the limits and the potentials here. And part of this is also due that the literature is sometimes quite different. So a lot has been, not a lot, but some things have been done in computational statistics and epidemiology, but sometimes the terminology is quite different. So at least I am sometimes a bit lost in translation. I feel it's super important to translate these things and to join forces here. But that's not always an easy task. And this brings me to my last issues. In the very end, most of the people here are working in the social, behavioral, maybe neuropsychological sciences. So we have to ask the question, what's in for our discipline? Do we really get better from data to causes if we're adopting these things, or is this just some mathematical finger exercises? And ultimately, will it improve our science and our knowledge? So with these open questions, I thank you for your attention, and I thank my collaborators. Obviously, this is joint work here with lots of people, most importantly, the ones you see here. And again, I think we have time. Christian or Mike, I hope you were looking at the clock, but I think we're in time and we have time for one or the other question.